Hello everyone, Tony here. In this video, I want to talk a bit about USB and how the USB protocol works, especially with the tree hierarchy, because I think this is something that's a little confusing. When we see product launches such as AMD's upcoming Ryzen series and their motherboard chipset, and they talk about how their motherboards will have 14 USB 3 ports, I think a lot of people assume that like each USB port on a computer is independent. So if I have 5 USB 3.0 ports and each USB 3.0 port is 5 gigabits per second, by the way, in this video, when I say USB 3.0, I'll talk about the 5 gigabit per second standard. 3.1 has 10 gigabits per second. 3.2 has like 20. I think they're like 3.2 Gen 1, 3.2 Gen 2, Gen 3, and like same with 3.1 nonsense is very confusing for consumers, and I think it just makes sense to call it like, hey, USB 1.0 full speed is 8 megabits a second, 2.0 is 480, 3.0 is 5 gigabits, 3.1 is 10 gigabits, so on and so forth. I think that's probably a lot easier to understand. As I was saying, if your laptop has 4 USB ports and each USB port can do, say, 5 gigabits per second, say it's a slightly older laptop, a lot of people assume that that means that, hey, 5 times 4 is 20, right? So I should be able to get 20 gigabits per second of connectivity. But this is actually not how it works. And I'll talk about why. And it's because it's because of the way how USB is a bus and the way it's kind of laid out in a tree. It's not even a true bus anymore. It is mostly a tree because it's hubs on hubs and hubs. But actually, how many, like your total bandwidth available to USB doesn't depend on the number of USB ports. It depends on the number of USB root devices. And the root device is essentially that can interface with the CPU and convert it into like a primary original USB port. So most computer chipsets actually will have about 2 USB roots. So for example, on the ThinkPad that I'm recording this video on, there are 2 roots. One is used exclusively for the webcam, and one is used for all the other USB ports. Well, one is used for the webcam and Bluetooth. That's a USB 2.0 root. And then the USB 3.0 and other second 2.0 root are used for the USB ports. And by the way, yeah, USB 2.0 and 3.0 actually end up connecting to different root devices because they're not fully backwards compatible. We'll discuss how that part of it works as well. But essentially, the takeaway from that is that your 2.0 and 3.0 bandwidth are completely independent. So 2.0 is 480 megabits per second, whereas 3.0 is 5 gigabits per second. But if I have 10 USB 2.0 devices, that doesn't mean I'm out of USB 3.0 bandwidth. They actually don't, like, they're independent of each other and they're not sharing bandwidth. They go to separate root devices. What does go to the same root device is if I have multiple USB 3.0 devices or multiple USB 2.0 devices. And that just depends on how many roots you have. A lot of you have probably also heard of or used USB hubs. These are devices that can take one USB port and change them into multiple USB ports. See, that's kind of what's actually happening inside your computer. And we'll start with a simplified example with a single USB root, and let's go from there. Let's say I have a main computer. So let's start with USB 2.0 for simplicity, and then we'll talk about 3.0 later. But say this computer is a single USB 2.0 root device. Say I want to then connect a mouse, a keyboard, and say I want to also connect like a webcam. All of these are going to connect to the single USB 2.0 root. Now, this is the electrical representation. Physically, we can talk about how the computer, probably you're not connecting them to the same port, right? You almost certainly have multiple USB ports on the computer. And each of these is plugged into a different USB port. However, behind the scenes, all of these USB ports are actually just connected to one internal USB port. So this is what I mean by the tree structure. Suppose I have my computer over here. It's got its monitor, and say it's a desktop computer. And on the front of the computer, we've got like 4 USB ports. And let's assume for simplicity that each one of these USB ports is actually USB 2.0. So I probably have multiple devices that I want to connect here. So say I take one USB port, and that's going to go to my mouse. Second port will go to a keyboard. And let's say a third one goes to a camera. So I have 3 devices here, and physically they look like they're connected to 3 different ports. Electrically, however, that computer almost certainly has a single USB 2.0 root. By this I mean this is what connects to the CPU. So let's draw our CPU up here. And the CPU primarily uses PCI. It uses PCI Express to talk. So the CPU will have PCI Express probably connecting the USB root devices. Again, this depends on how the motherboard and whatnot are implemented. Realistically, if you don't have add-in USB cards, what's probably happening is the CPU is connected to your Southbridge chipset, and your Southbridge chipset is what provides the USB route. But for the sake of simplicity, I'm not going to include the Southbridge chipset. Let's just assume that the CPU is what creates the USB root device, because that's essentially what's going to happen here. And then from this one root, we actually will have three devices. The mouse, keyboard, camera are all actually connected to this one USB 2.0 root device. Now you might say, okay, like, what's the problem with this? It works. Why would we need to do something more than this? And for actually only having these three devices, if like the camera's off, there will actually be no problems. And even if you have one webcam that's running, you will have no problems. This will work. But what you need to remember is that USB 2.0 is 480 megabits per second. But that's not 480 megabits per second per device that's connected. That's 480 megabits per second at the root. So this over here has a maximum of 480 megabits available to it. Now, mouse and keyboard, they really don't take up that much. They probably don't even take up a megabit. You'll probably be fine even with like USB 1.1 for those. The camera though, the cameras can take up quite a bit. A typical, you might have noticed that on webcams, there are usually different resolution options and different video encoding options. For example, most webcams do actually support UV video, which is lossless, so like raw video. However, you'll almost never see someone using it because with 480 megabits per second, the maximum you can do over UV while maintaining 30 frames per second is 640 by 480 essentially, which, I mean, it's better than 240p, but it's not HD. And the problem is that USB 2.0, like there simply isn't the bandwidth to send full HD RAW. I'm recording this video at 1080p 60 RAW, and I have to use a USB 3.0 port to do it because it takes way more than 480 megabits per second. Essentially though, one webcam, say it's running, so anything above 480p almost always is MJPEG, that's why I brought this up, and say it's doing 1080p 30, it's using like 250, 300 megabits per second. So this can be using, let's say, 250 mbit per second. And there's like 200 left for these devices to share, so it's fine. Now what happens if, say I want to do a stream or I want to record a video with multiple camera angles? So I'm gonna take this and I add a capture card, like HDMI capture card here, or a second camera. Well now this also wants to, if this is one of the cheap macro silicon cards that I might have featured on this channel, those are USB 2.0, they use MJPEG, and they can also send 400 megabits per second. So say this camera wants to send 250, and now this wants to also send like 400 or something. I think you can see where the problem is. We cannot actually have both of these on the same network. Now someone might look at the package, and even if these were this was also like 250. Now of course by 250 I'm referring to 250 megabits per second. The same thing applies for 3.0 when we're talking about gigabits, but I'll get to that in a minute. Like, these cannot be running off of the same port because there simply isn't enough bandwidth because like the bandwidth is being shared between these. There are some other interesting quirks with the way this tree works, and I'll get to that in a minute. But essentially to do this, what you actually need, you want your CPU to have a second USB 2.0 root. And this root device, you can then get its own 480, and I can then connect my second card, for example, over to here. And this way, this can do 250, this can do 250, and it's perfectly fine because they're going through these different adapter cards and root devices. So this actually becomes a problem when people try to do stuff with VR, for example, where each tracker wants to use multiple gigabits per second on a USB 3.0 port. And you simply can't have that. So for example, let's draw that example out. On those computers, say you also have a mouse, keyboard, and webcam connected to USB 2.0. Now, as I said, USB 2.0 and 3.0 roots are actually completely independent of each other. So I can have a 3.0 card on the same like port essentially as these, and it will be fine. These 2.0, like even if this was using 400, that 400 is not deducted from the 3.0 bandwidth. The 3.0 bandwidth is available just for the 3.0 devices. And that's partially because USB 3.0 has 3 pairs of wires. One is like for data, one is the standard TX and RX used on 2.0, and the other two are special and unique to USB 3.0, and that's what gives it the extra bandwidth. But so this on most modern computers will be your USB 3 root. And you can actually see this on Linux if you run ls USB, it will give you a printout of all the devices that are connected over USB. And in fact, it will tell you if it's on 2.0 or 3.0. And if you do ls USB -t, it will give you a tree printout of exactly which root device each of these devices are connected to. So again, that's ls USB -t, and you can find out how like your devices are actually wired. But say I have my 3.0 root, and I want to have one valve index tracker. Okay, so maybe this wants like 2 gigabits per second, right? I don't know the exact numbers. Say I have a second. This also is going to grab 2 gigabits per second. If I want to have a third one, though, I think you can see where the problem is. You can't. And in fact, even these two on one root will probably start to malfunction because of the aforementioned collision issue. Like to run both of these, you will probably want to have two distinct roots, one for each, just because 2 plus 2, yeah, 2 plus 2 is 4, which is less than 5. But also each of these has, like the more devices you add, the more overhead you need in case there's either buffering issues or so on and so forth. So you need to leave a buffer. This is why, for example, I cannot have two cameras using 200 megabits per second on one USB 2.0 route. Because 200 plus 200, yeah, it's 400 less than 480, but chances are realistically you're gonna start like either losing frames or weird quirky things are gonna start happening. And if you don't want to deal with the hassle of that, probably just best to add yourself a second root. All right, so you might be thinking, all right, Tony, like I see the point. Multiple roots, good, okay, like, you know, but what to make of this? How do I get these? So as I said, on most systems, you actually probably already have two, and it's worth checking. Run the ls USB-t command, see how many USB 2.0 and 3.0 roots you have, and try just moving stuff around on your motherboard. Sometimes the top two ports will be on a separate route. Sometimes on my motherboard, for example, it's the middle two on the back that are on their own, and the top and bottom two are actually sharing one USB hub. So there's a lot that's mixed and depends. Maybe your front I/O is on like a different one, so on and so forth. As I said, on this laptop, for example, the webcam and Bluetooth get one, and the ports all share the other, which is, I mean, it makes sense given that, as I said, an HD webcam can easily use 200 megabits a second. And people are probably going to use the laptop webcam. However, this means that if I plug in an external webcam, I can't run another high bandwidth application. For example, I probably cannot run both a hard drive and a USB webcam if it's using USB 3.0, because those two are going to steal bandwidth from each other. But I can have a USB 2.0 webcam and a USB 3.0 hard drive, and that's almost always fine. So how can you actually add more root devices? Well, if it's on the chipset, you can't. Like, you can't go and be like, hey, I want the chipset to have more of this or more of this. Like, the chipset's kind of like baked into the motherboard. You don't have as much control there. So if you're on a laptop, you're kind of out of luck. And like, no, you cannot convert a USB 3.0 port into multiple 2.0 roots. It doesn't work that way. The latencies and whatnot would make that simply unfeasible. So if you're on a laptop, you're kind of out of luck. There isn't too much you can do, unfortunately. You can try to manage what devices are plugged in better. Maybe don't run two external hard drives at once, or like figure out how the laptop's wired. But yeah, a lot of it's going to be limited. Now, if you're on a laptop, there might be one savior for you, and that's Thunderbolt. So if you have a Thunderbolt port, Thunderbolt uses PCI Express. And if you have a Thunderbolt dock, chances are it's actually not using the USB mode of USB Type-C. Because USB Type-C supports many different alt modes, and maybe I'll talk about that in some other video. But in short, a USB Type-C port can be USB 2.0, 3.0, 3.1, 3.2, so on and so forth, all the USBs. But it can also carry HDMI. It can also carry DisplayPort. And also, if you have a dongle that has an HDMI port, chances are it's actually using DisplayPort and converting it to HDMI in the adapter, because the HDMI alt mode isn't supported on all devices. Notably, a lot of ARM devices will only let you use the DisplayPort alt mode. And if you're using HDMI, they will want you to use the HDMI MHL mobile link standard. So yeah, there's a lot of interesting ways that it can be wired. But the one that's important for this application is the fact that you can use Thunderbolt. And Thunderbolt, as I said, sends PCI Express lanes over USB Type-C. So this means that if I have a Thunderbolt dock, it can actually use PCI Express, and which, by the way, if you're unaware, so the reason PCI Express is good is because PCI Express is a direct link to the CPU. On most systems, you will have 16 or 20 PCI Express lanes going from the CPU, and you will have like another 4 or so coming from the chipset. And that's what will run things like your Ethernet or whatever. Unless we're talking about an SoC, in which case most SoCs aren't really big on having a lot of PCIe connectivity. They'll maybe have 1 or 2 PCIe 2.0 ports just for whatever devices you want to put on it. But that's because SoCs typically will have Ethernet built in, cameras will use like MIPI or the SIPI standards, like they'll all be baked into the SoC. Whereas on things that aren't SoC, anything you want to add, like your motherboard, you want to have an Ethernet port on this computer, guess what? It's going to use either a USB to Ethernet adapter or a PCIe to Ethernet adapter. And of course, the PCIe ones are much higher performance. So generally, you'll use PCIe X1 for a gigabit Ethernet port, for example. 100 megabit can be done over USB 2.0. If you need gigabit, you can also technically do 3.0. But for example, the early Raspberry Pi iterations did not have built-in Ethernet, actually using USB converters. This is why they weren't very high performance, because you had to convert USB 2.0 to 100 megabit Ethernet. Whereas on the Raspberry Pi 4, for the first time, the Ethernet port is connected over PCI Express. And this is why you can get much better performance on that port. And also Wi-Fi uses PCIe as well. But basically the point is that PCIe goes straight to the CPU. So if you have a Thunderbolt dock that's using PCIe, chances are your USB ports are actually going to be pulled from PCI Express, which means that it's a completely new root device. Because we've got PCIe going from the CPU all the way to the root, and then that's what's creating your ports. Now, I think this leads very well into what you can do on desktop computers if you need multiple USB roots. I think given that I was speaking about how PCIe works and how PCIe might be good for this, I think you can see where I'm going. Desktops are generally in a much better space because they give you free access to the PCI Express lanes. And unless you're working with mini ITX, where you only got one PCI X16 that's probably going to a GPU, even MATX will often have at least 3 or maybe even 4 PCIe ports that you can use. And so what you can do is you can easily get USB 3.0 to PCI Express adapter cards. Generally, these PCI Express adapter cards will take up one lane of either PCI Express 2.0 or PCI Express 3.0. And they will then be able to convert this into up to like 4 different USB routes, because one lane of PCI Express has many gigabits worth of bandwidth available to it. There are a lot of cheap adapter cards where they will have either 4 ports or up to, I've even seen some with 7 ports. However, that's all kind of interesting because they only have one route and then they're using a USB hub to be able to get 7 ports out of it. And we'll see how hubs work in this model. They work exactly as you would expect with the multiple USB ports example. They're just like, these are connected to a hub essentially, but they can take one port and basically branch out the tree. So they'll take one root element of the tree and give you access to multiple different child elements for that tree. For example, StarTech has a PCIe card that I'll link down below, which is one of the few I've seen that actually will give you 4 separate or 2 separate USB routes, each with 2 ports. And that's great, again, if you want to run something like a VR headset or something where you actually need the bandwidth of having multiple USB routes. Otherwise, a lot of these cheap cards, unfortunately, one route is better than nothing. They'll add one, but those 4 ports that they're adding will be 5 gigabits per second total, not 5 gigabits per second per port. Unless, as I said, you can get lucky and find some magical card. And there are a lot of vendors that make these USB to PCIe adapters. In fact, a lot of motherboards ship with them. Like I remember my desktop's Asus motherboard, for example, for Haswell, which Haswell only provides like 4 USB 3.0 ports from the chipset off of 2 routes. But the motherboard had more, and the way they did that is like ASMedia, Fresco, Logic, a bunch of these companies make PCI, and Realtek, for example, is another massive one, make PCIe to USB adapters, which are generally used in these cards. So if you're on a desktop, you can go to any computer store essentially, and you'll be able to find lots of these adapter cards, which will take up usually one lane and give you more USB ports. And you're guaranteed that even if the 4 ports are on one route, you're guaranteed that you're adding at least one USB route to your system. And you'll be able to see that when you're on LS-USB-T. You will see that it adds a completely new bus to the system. And that's great if you want to be able to run multiple things in parallel. So I can have one camera connected to my motherboard's USB, one connected to the PCIe card, and now both of them can run happily and not interfere with each other and not run into bandwidth limitations. So I want to make a note on USB hubs, since that's something I mentioned. Essentially, these are all hubs. So a USB route would essentially have only provided one lane, right? So if we draw this computer out here, there's only one route, which means I would only have been able to plug one device into this. But of course, you want more than that. So for example, a 4-port hub, let's just draw out a 4-port hub here, takes this one USB port and gives you 4 more. And in fact, the input to this hub doesn't have to be the root, right? I can take one of these ports, say I drag one from here, this is like one of the ports on my motherboard, I can put a hub here and say this is another 4-port hub, so that would give me 4 more devices that I can connect. But of course, we've just added more child nodes to this child node of this tree. And in fact, you can connect another hub here, so on and so forth. You can, I think, daisy chain almost like 100 hubs with USB before stuff really starts to complain. Obviously, I think you can see why this might not be the best idea, given that what you know now about the fact that this is all sharing the bandwidth of that one root up there. Because basically, there's already one hub, right? The one here and the one that I represented up here. Those ones are already built into your motherboard. That's like the multiple ports. You have 4 ports. You don't have one port on your computer, you got multiple. That means there's already at least one hub which has taken the one output that's connected to the CPU and given you multiple here, which is this, right? And technically, there are multiple hubs because you'll have one hub for USB 2.0 and one hub for 3.0. And the 3.0 ports have to have both so that you can use either, right? You can plug in USB 2.0 devices to 3.0 ports and they work. And this would be something I plug in. So say I'm out of USB ports, so I bought like a hub on Amazon, plugged it in. This is what that gets me. That gets me 4 more, so I can plug in 4 more devices. And well, we'll see the limitation of it. So say, for example, here, I then decided to plug in a hard drive, all right? And here I was going to plug in, say, a little SSD with some NAND flash on it and a controller or something, right? These are going to share with this, and say one of these was like, just to add some variance in here, what's another USB 3.0 device that can hog a lot of bandwidth? Of course, hard drives, those are one of them. Say I had a display link, like USB-based graphics card here. Not a very good representation of a GPU, but like say we had a USB GPU there, that's gonna also wanna pull a lot of bandwidth for itself. Let's see how these communicate. So this isn't a true bus. A true bus would have been something like this, where the computer is here, and that's a bus. And device A is here, device B is here, C is here, D is here. That's a very traditional classic bus topology. This is very common. For example, Ethernet and networks used to use Ethernet hubs before Ethernet switches became really popular. And an Ethernet hub is basically this. It's basically just a splitter. Now, this means that when A talks, D shouldn't be talking, right? But the thing is, D doesn't know when A is going to send its own packet out. So, and if D and A send a packet out at the same time, that's a collision. So devices actually have to be somewhat careful to make sure that they're not talking at the same time. And with networks, this is solved with CSMA. And there's CSMA CA, which is collision avoidance, and CD, which is collision detection. And for example, Wi-Fi has to be actively ensure that there's no collisions. Ethernet, we can get away with collision detection, where if we detect, we just send it, and if they collide, well, we try sending it again. And if they collide again, wait a little longer and try sending it again, so on and so forth. That's how Ethernet works. But essentially, that's what happens when everything is on one collision domain, because these are all sharing the same. This is a very traditional bus topology using Ethernet hubs and whatnot. And you will now know that, for example, every Ethernet hubs have pretty much gone extinct because everyone has started switching over to Ethernet switches. And the advantage of an Ethernet switch is that they're not wired up like this. In an Ethernet switch, A, B, C, D all talk to some backbone with a CPU. And a switch will have a rated switching capacity. Generally, for a duplex switch, that should be double the number of ports. So if it's a 4-port switch, I would expect that it would, and these are all gigabit ports, that switch should ideally have an 8 gigabit per second switching capacity, which means that without collisions, it can route if each of these were at 100% utilization, A is talking to B and C is talking to D at the same time, in both directions, it would work. And we wouldn't run into problems. But, so that's basically each port gets its own collision domain, and we don't have to worry about, hey, A talked at the same time as D. A can talk to B, C can talk to D at the same time, and everything is fine. But that's an Ethernet switch. We're not talking about Ethernet today. Today we're talking about USB. And we can talk about other differences. For example, Ethernet's great at long distances, right? Like I can run Cat6 for 1,000 feet. Good luck running 1,000 feet on USB 3.0 and getting like any bandwidth over it. In fact, with USB, you generally need to start getting into active splitters pretty quickly. So it's something to be wary of. Now, back to the point is that USB, there was a particular decision that was taken about whether the devices should be smart or whether the hubs should be smart. And basically the consensus was that, well, there's not going to be very many USB routes and there's not going to be very many USB hubs, but there's going to be a lot of USB devices. So like if we make the USB devices themselves really dumb and we make the hubs and route a lot smarter, this will be a lot more efficient because then we can get away with putting like chips to like do what it's supposed to do here, and each device can just like think that it's talking to the root or whatever. So we don't have to like put any expensive logic here. All the expensive stuff is like, we have less of the expensive things and more of the cheaper things basically, which is, good economics. Also good engineering, I suppose. Here's how it works. My computer here with the CPU wants to send something, I'm like downloading this video from my PeerTube instance, which hopefully will be up by the time you're seeing this. It's been undergoing maintenance. Also, my server's kind of out of disk space because it was a very small server. So let's assume that you're downloading a file from like my wiki or from my website or something, right? And you want to save it to this external hard drive. So your CPU and your RAM, like all of that has determined like the file is now in your swap space, right? Like it's in your RAM, it's in the buffer, it's ready to get written to the hard drive. What happens? Well, the CPU, so each of these USB devices has a particular ID that it's given. So it's a bit like how with Ethernet devices that I was referring to, each device has like an IP address with the global internet, right, to get from any point to any point. But locally within a network, they also have addresses. That's the MAC address. And that's how, for example, if things are on the same bus, you know that like computer A doesn't you know what's going where. A is talking to B versus A is talking to C. Because if A was just like saying something, well, the other device would be like, is that for me or is that like for the other person here? So instead, we use the MAC addresses, and that's a layer 2 link layer protocol, so that things know where which device they're talking to. USB is kind of similar to that, where each of these USB devices that we have here is given an ID. And so that ID will make sure that like the device will know, hey, is this actually something that's coming to me? Or is this something that I should like be ignoring and it's actually because it's talking to someone else? I appear to have overlooked bringing multiple colors of markers, so we're gonna have to do this with one color. CPU knows that this is on the USB 3 route, okay? So it's smart enough to know like, okay, it's not gonna send the data going to the hard drive over this route. So it'll make its way up to the correct route that the device is on. But after this point, the CPU doesn't actually have a direct connection anymore to the hard drive. So what it does is it sends essentially what is the equivalent of a broadcast. It sends that data out to everyone. And these devices can then have like the cheap detection logic. They don't have to know like which way it's routing. They just have to be like, hey, is this coming to me? No? Okay, bypass it. Coming to me? No? Okay. And then it makes its way to the hub. And we then say, hey, is this device connected to the hub? Well, the hub may or may not know. So if it doesn't know, what it's going to do is the hub is going to forward it to all 4 of its child ports and say at another hub. And those are going to forward it. And it's essentially going to make its way to all of these devices. And when it gets to this device, we're going to say, nope, it's not for this, not here, not here. And oh yeah, it is here. So like this is what we want. So when something is talking down, so you're going, again, this is computer science, so the trees are going top to bottom. Essentially, the CPU has sent it everywhere. So it sent it to this, which has sent it to all 3 of its children. This had full child nodes, so it has sent it to all 4 of its child nodes. And if I had another hub, this hub will say connected to this port. This will then forward it to all of its children. So basically, any message sent by the CPU goes to every single leaf node. And what I mean by a leaf node is like a device that's plugged in. So that's what I will consider the leaf. In the middle, we have the hubs, and we have the root at the top. It made its way to every single leaf node or device that's here. And the hard drive goes, oh, hey, yeah, that's me. This data is for me. And it can then save that to the disk. And we can repeat the same thing. Say this was actually wanted to talk to the external GPU. While it comes here, the VR headset ignores it. The GPU is like, yep, that's for me. The tree might forward it, or the hub might forward it to all of its children. And these devices will all ignore the packet. And the devices can know whether, hey, this is for me, or like, is this a packet that I should ignore? Now let's talk about what happens when it's backwards. I have a device, and the device wants to talk to the CPU. So say I have my hard drive here, and say now that like the video is being downloaded and saved, let's say, the user wants to actually watch it. So they pull up VLC Media Player, and they open the video. Now the data has to make its way from this hard drive up to the CPU. The CPU has to first talk to the hard drive, right? Like there's a lot of control here. And the CPU has to be like, hey, I want this file that is in like, depending on if it's like host managed or drive managed, one of the two will know where that file is. So like first this is gonna pull up, like if it's a FAT32 or something, it's gotta pull up the file allocation table, so on and so forth. But I'm skipping like that negotiation step of like, first let's figure out what the inode is or the inode, and then like let's like look it up in the file allocation table, and like let's go there to that block. That's all preamble. The preamble works in exactly the same way, by the way. The CPU, if the CPU wants to tell the hard drive, hey, I want you to seek to the sector number, it cannot talk to the hard drive. So like that seek command is actually issued to every single connected device, just like what we said in the earlier example. And if the hard drive's then replying, okay, yes, I have seek there, you can now get the data. It goes up. And we're assuming that we don't have DMA being direct memory access. I'm going to assume that they're going through the USB protocol. What's going to happen here? So the hard drive is going to start, then once the preamble's done, say it's actually sending the data, say it's sending the file, right? So this is sending the file up from it, and it goes to the hub. Now the hub receives it. What's the hub going to do? Well, if this was a vintage Ethernet hub, what it would do is it would just send it to all four of the, well, it has 5 nodes essentially, but as I said, on Ethernet, that's equivalent to this. If this was an Ethernet hub, it would have been this classic bus topology where there's no one that's driving the bus. So the parent is treated exactly the same as the children. And it would essentially, the hard drive goes here, it's actually going to send to every single one of the 4 nodes. But as I said, with USB, the smart logic is in the hubs, and the devices themselves are have minimal logic. So the hard drive sends it to the USB hub, and the USB hub knows what the parent is and knows the 4 children. And so the hub knows that, hey, there's no reason for me to send this down because it's coming into me from the child nodes, right? The hard drive is sending the data to the hub. So what the hub will do, the hub then says, okay, I'm just going to forward this up. There's no reason for that it would send it down to the other ones, so it doesn't. It only goes upwards. And then that goes to this hub. And that hub can be the one built into the motherboard, and it says, hey, this data is coming from one of the child nodes, and it's clearly not going to these. It's trying to talk to the CPU. So it says, okay, we're only going to forward it off to the CPU. So the data, when it's going upwards, essentially will actually just draw a single line. It'll go hard drive to hub, to other hub, to CPU. Stuff going downwards is essentially broadcast. It goes to every single one of the leaf nodes. But stuff going upwards is smarter. It'll basically just take the path that's going up. Example 2, say I ran another hub here or something. This goes to my desk. And say it's like a 2-port hub. And I have a mouse connected here. And I have a little flash drive connected here. So the mouse is either it's doing polling or it's doing interrupt-based logic. We can talk about the different modes of operation for USB mice and keyboard some other time. But in short, mouse wants to talk. Okay, mouse is going to send it to the hub. Hub knows, okay, forward it up. This hub is going to forward it up to here, which is going to go to the CPU. But then say the CPU wants to write over to the flash drive. It's going to go all of these and all of these. And each device will basically just check, hey, is this for me? If not, drop the packet. If this computer, as I said, is going to talk to this USB 2.0 device, that packet does not ever go to the USB 3.0 route because they're independent. It's going to only go to the USB 2.0 route, which is then going to send it to all of its children and all of its children. It's only going to make its way on the USB 2.0 side of things. All right, and I think that's all I wanted to bring up for this video that got a little longer than I wanted. It looks like we've been going for 40 minutes now, talking about how USB works and the USB tree. Hopefully you enjoyed this video. Hopefully you learned something from it. And if you enjoyed this video and you'd like to see more like this in the future, please consider leaving a like or subscribing to my channel. Helps me out a lot. Thank you so much for watching, and have a great day.